Welcome back, everybody. Yeah, I apologize that there were a few typos for the slides for the last exercise, which I'm sure didn't help. But yeah, I hope you still learned something and had some fun with this at least. Now we are pretty much diving back in where we left off, because we had this very fair question asking us where these sparse dimensions come from, like if they just appear out of thin air, and thin air being the driver code in this case, or whether we have also a means of manipulating them within Dusk. And it turns out that there is kind of like two perspectives on this. Like if you have sparse dimensions which only depend on the geometry, you could basically also say that this is responsibility of the meshing library, and this belongs under the hood. However, if this is not the case, and we have sparse dimensions, which, for example, are different in each time step, then we could not cop out here, and we would need to offer a concept within Dusk to manipulate and fill a sparse dimension. And it turns out that in Icon, this is in fact not the case. So there are sparse dimensions, which are, for example, dependent on velocities. So they are dynamic. So we also need to be able to address this within DSL code. So here, this would be a real-world examples lifted straight from the Icon source code, where we can see the sparse index here. So here, it's like the sparse index in the name, because in this situation, the developers decided to isolate this into 4 individual fields. But we, within Dusk, would model this as one sparse field. And here on the right-hand side, you can see actual sparse dimensions in Icon with the sparse index last. And here we have the neighbor table, which you might know from last exercise, which goes from edges to cells and then to vertices to yield 4 neighbors. So the 4 is here right at the bottom, and then it's snipped off because of space on the slides. So here is what the same code would look like in Dusk. So we have the VN word, which is our sparse dimension, and we use the with sparse concept to fill that sparse dimension with contents given by other sparse dimensions, these primal normals, which are on the edges of a diamond, and dense fields U and V, which are just located on vertices. So again, we are looking at the generated pseudocode, and I realized that this gets a little out of hand with regards to the indices. So let's have a look. We have the edge index, which is given by what we call a stage, which is a result that the first element of the chain is a edge. Then we can also generate a neighbor index, which is the vertex index, because this is the last element in the chain. And then we obviously also have this sparse dimension, which we intend to fill. And a sparse dimension always needs this linear index, this case going from 0 to 3 or from 1 to 4, to actually fill it. But before, you only have seen this index on the right-hand side of the assignment. And in this case, it just also appears on the left-hand side. Okay, so now this would be an excellent opportunity to look at the example from before the break again. But this time, we are not only interested in performing the evaluation of the interpolant, but we are also interested in actually filling the sparse dimension containing the function values here. So I chose an arbitrary neighborhood because the stuff up there is supposed to work for any possible neighborhood. So we are going from a cell to a vertex, from an edge to another vertex, why not? And yeah, I was a little bored to make an animation again, so I hope this is still clear. We start at the cell. We encounter the 3 vertices at this inner ring, so to speak. And from there are quite a few edges to visit. And from there, we add kind of like this outer ring of vertices, which I believe gives 5 plus 7, 12 neighbors to support this interpolation. So here I picked a function for which this happens to work. Why exactly this works is maybe a little bit beyond the scope of what we are discussing today. But please trust me that this will work out. So one thing you can see here in this code to fill this sparse dimension, which is supposed to contain these weights after we are done, is that we have the opportunity to introduce an intermediary result in this case. So the with sparse statement is actually able to support a list of statements or a block statement in its body, which is contrary to the reduce over statement. Yeah, this is this like what I just described, that we have this temporary result. And we need to declare this for now. So this needs to be declared as a field with the proper dimensions, because currently we have no support for just a local variable within a loop. Okay, maybe a little bit embarrassing, but you've already seen this in the exercises. We do not have globals. So we need to emulate this parameter h and the mathematical constant pi by global fields. So we're wasting some memory here, but this will be fixed soonish. Okay, and then we can go one level further. Let's do the whole thing. And this is what we have here. We have now the code filling the sparse dimension and the code consuming the sparse dimension, right, wrapped into one kernel. Also computing this normalization factor with this reduction on the bottom. What else can we see here? Well, we can see that we had these fields in the API, but probably nobody else, so to speak, is interested in these intermediary results. So we demote them, so to speak, to temporary fields, and then we get a clean API. And this would be a quite general interpolation stencil implemented in Dusk. And here on the next slide, we can see something else, which is maybe worth demonstrating in Dawn. We have this intermediary field on a cell, but it turns out this field is never at rest horizontally offset. We never look at neighbors in that field. So what this means is that from a single thread, from the perspective of a single thread, this doesn't even need to be a field. And this is actually something Dawn is smart enough to recognize. So here Dawn would notice that this is never at rest horizontally offset. So it would demote this internally and never even allocate a field for that, but just put a float variable in the generated code. So this would be the CUDA backend, not that you need to understand it, but just that you have seen it at least once throughout all of these presentations. Okay, and here we just have a picture to inspire some confidence that this stuff is actually working. So here we have the source points, so to speak, which are residing on the vertices. And here we have the resulting interpolant, which doesn't even look half bad if you ignore the boundaries. All right, so we have talked quite a bit about sparse dimensions now. What we didn't really touch upon, at least not formally, is their types. So you have seen that they have this neighbor chains in their type, which is opposed to the ordinary fields, which just state a single location. And now we're going to have a look at what this actually implies. So here we are taking one step back, and we see that we have two assignments. One's assigning a cell field to a cell field, and one's assigning an edge field to an edge field. And here on the right-hand side, you have the generated pseudocode. So here we need to generate two subsequent for loops. And now assuming we would allow something like this, where we would have this sparse field f and we just multiply it in there. And now the question is, can you assign valid semantics to this example? So here is a proposal what we could generate in this instance. But if you look at this, at least briefly, you will see that only ever the last entry in the sparse field will matter and the other entries will be ignored. So this is clearly not meaningful code. I mean, this is extremely awkward. This is certainly not what the user implied when doing that. So maybe the user implied that this should be summed up in the sparse field, but then the sign here doesn't reflect anymore what's written in the code. So this is clearly a too horrible idea to entertain. So that's why we restricted sparse fields in the sense where they can appear. So they can only ever appear in a reduction expression or in a with sparse statement, because only in these contexts it is very clear what we mean when accessing the sparse field. And this also makes the type rules quite simple, because then we have this sparse field with a neighbor chain and we have the reduction with a neighbor chain. And basically these two things need to match. And here also the intention is clear. We're saying sum over, so we generate a sum. The same goes for the with sparse statement. So with sparse statement implies that we want to fill, so we generate an assignment. And again, we can type check that the sparse field has the same neighbor chain as the with sparse statement. So the semantics are completely clear and we generate meaningful code. Yes, this is just reiterating what I just said, because I forgot that I have separate slides for this argument, but I think that's clear either way, right? Now, what is maybe less clear is that we have now this sparse field and it's in a reduction, so fair enough, we may use it. But maybe not immediately clear is what other kind of fields we may combine it with. So we have this sparse field here. We have the edge field where we want to store the results. This is not particularly relevant now, but we have another edge field, another cell field, and a vertex field. And we are wondering which fields we may use in this multiplication. So this is obviously fine because of the chain. So, and now basically the rules follow. This is also fine because edge is at the start of the chain. This is also fine because vertex is at the end of the chain. However, this wouldn't be fine if we use the cell field, which is in the middle of the chain, because for this we cannot generate meaningful code. So here again, just to reiterate, this is probably the maximum you can do in this case. You can multiply the vertex field as well as the edge field. And maybe to drive this home, it helps if we look at the generated code again, and maybe it helps if we also highlight the indices again. So we have the edge index, which is spanned by the stage. We have the vertex index, which is the kind of neighbors we are iterating over. And we have the linear index to address the sparse field. But when you look at this, you realize that we never we never take care of any cells. Like this chain implies that we are only looking at the end, at the type which is at the end of the chain. We're only looking at vertices. So there would kind of like constructing the argument backwards. If you generate this code, that wouldn't even be a means to address this cell array. So the exact same goes for the with statement. So I'm not going to develop this further. This means that you're not allowed to fill this with the cell field in this case. Okay, I believe this is just the same developed again for the with statement. where we have the same, except that the linear index is on the left-hand side now. Okay, I realize that this gets a little bit repeaty, but let's look at one last example, if you want to bear with me. So here we have an edge field, and we have a sparse field going from an edge to a cell to another edge. So what do we generate here? So we realize that we have an edge index, and our neighbors are also on edges. So should we now take the inner or the outer edge index? So we see that the situation is ambiguous. And, well, the user could reasonably expect either index. There is no right or wrong here. So Dawn recognizes this, and it asks the user to clarify. So that's why we have this explicit horizontal offset concept. So if you want to have the outer index, you would just state edge, because, well, that's the start type of this neighbor chain. However, if you would want to have the inner index, you state the whole chain to express that you expect this field to be addressed with the inner index. The same is true for reductions. Just like you can formulate such a chain for a with sparse statement, you can do the exact same thing for the sum over statement, which we have developed with the exact same arguments here. Okay, so to summarize, in non-ambiguous cases, you may use these horizontal offsets. So it's perfectly fine to write it like this if you have a chain which is non-ambiguous. So you may state this if you want. However, in ambiguous cases, you are required to do it. There is no default. So if you forget it here, then Dusk is gonna complain and tell you that there is a syntax error. However, what you may not do, what you may never do, is you may never write a horizontal offset, just like it's forbidden to write a vertical offset in a write. So here Dusk would again complain with a syntax error that your horizontal index is used outside of a neighbor iteration. Okay, so this concludes our chapter for typing. Our next, a little bit smaller chapter would be about nesting reductions. So this is in an early stage. It's not very well tested. But we understand that meaningful semantics can be assigned to nested reductions. We don't have a very clear idea how to code generate this for CUDA currently, but I mean, there is nothing blocking us from eventually doing it. And the reason why we didn't do it yet is because there does not seem to be an apparent use case in the icon die core. Might be we have missed it so far, but we don't think that in that part of the icon die core we are interested in, this is actually happening. But still, let's have a look. So this, what you can see here, is absolutely valid Dusk syntax. You just have a reduce over, which is nested with another reduce over. So we have our outer reduction, our inner reduction, which is executed 2 times because there are 2 cell neighbors to an edge. We need to type check this. So the first element of the chain needs to be equal to the last element of the outer chain, because the first element of the inner chain is also at the same time its return type. Yeah, because this needs to be type consistent, right? If we return in a cell here and B is a cell field, then this needs to be consistent because this is a binary operation. And here we have, in animated fashion, what happens in this case. Here we are executing the inner reduction. We are multiplying by the B field and get this intermediary result. And we reduce this onto the A field, which is located on edges. And now maybe the tricky part. We have nested reductions and we have chained reductions. Here we have a very similar example as before, but we made it a little bit less complex, like the B field is gone. There is no multiplication by B in the operands. So now a quiz question could be, I mean, I'm not going to open the floor for a quiz, but still you could ask yourself, is this equal? Or phrased differently, assuming C is 1 throughout the domain, what result would you get on the right-hand side and what result would you get on the left-hand side? So let's have a look. So again, we're doing the same thing as before. We are executing the inner reduction. We get the 3 on both of these cells. We do not multiply by B at this time, but directly reduce onto the inner edge. And we get the number 6. What happens if we do the chained reduction instead of the nested reduction? Well, we realize that there are no intermediary results in this case, right? We go to the vertices directly in a sense, and we reduce and get a 4. So here we have this side by side. Again, with the chain and with the nested version. So maybe another way to look at this would be here, the neighborhood is kind of like a set. Each element may only appear once. Whereas here in the nesting, these values on the side are double counted. So this would not be a set of neighbors in the strict sense. Okay, and now you're free to push the envelope, like you're free to mix, or to not only nest 1 level, but 3 levels or n levels deep. This is perfectly fine. You can mix nested and chained reductions. This is also fine. You can add some sparse dimensions in the mix, and then you can combine all of this to come up with monstrosities like on the bottom here. So I actually checked this. So this goes throughout the pipeline just fine and gives some result, which I expect is right, but I don't know what to expect here. So yeah, but I mean, I don't only want to brag that our pipeline is extremely stable because, well, it's not, as you have seen in the exercises. But the point I want to drive home here is that all of these concepts are composable and compatible. Like you're absolutely free to use them in any combination you want. And this is like arcing back to when I said that we wanted to implement this as generally as possible, such that we could anticipate very complicated reductions in the icon die core, or maybe further down the road in another die core. Another topic, well, actually the same topic, just like the reason why stencil inlining might be useful is I think the slides were slightly ordered wrong here. So this is again about stencil inlining. In this case, we have 2 stencils which are in fact equal this time around. One with an intermediary result and another one performing the same thing nested. And well, obviously the right-hand side might be preferable because we don't have this additional field, right? And actually there are also performance implications with inlining here. And also this inlining would be something which Dawn is able to perform automatically. So it's maybe not that relevant that this is representable in Dusk, but it's important that Dawn is able to do this. So again, this has performance implications, and we will see a lot more about performance tomorrow. So yeah, sorry about this little hiccup. I hope the slides should be fine after that, because we are also approaching the end of the second advanced topic block. What we want to talk about now is that in the beginning, we had these vertical offsets, right? Where we shifted one value down. And this is already quite useful because with this you can, for example, do finite difference stencils in the vertical. And this is sort of kind of general in the sense that you're allowed to go further. You can do a higher order stencil by using higher compile time literature. It's not only +1, -1, you're also allowed to use +2. But in Dawn and Dusk, we are more general than that. We allow you to use an indirection field which contains offsets. So which have offsets which do not need to be equal throughout the whole domain. And you can still combine this with a compile time literal. So I think here it becomes quite clear what's going on if you look at the generated code. So here we just explicitly added that we want to address this on the same level. So this is just the same as writing outdef equals inf. And if we put this indirection field, then what happens, you get an array access of an array access. And we simply look up the offset in this indirection field. And if we end the +1, we would get the +1 outside this additional nested array access. So some constraints. Again, writing offset, be it horizontal or vertical, is a big no-no. This is not going to work. And it's also obviously the same. If you not only do it like this would be even worse. So this is also prohibited. You're also currently not allowed to mess with an index field. So if a field is used as an index field, so sorry, this should read index field here, then it's actually protected from being written to. So if you actually need this, if you need to manipulate an index field, this is also a restriction that we want to lift eventually, is you need to split this. You need to do a detour through the driver code. You just make a prepare where you mark it as a usual field, and then when you consume it, you mark it as an index field. I also always want to give a little background why these things might be useful. So the classic use case for indirections would be semi-Lagrangian advection, in this case in the vertical. So in a first step, you would compute the backwards trajectories to get an offset field. Maybe just as a quick detour for the people not familiar with semi-Lagrangian advection. So what you do in semi-Lagrangian advection to advect a quantity on a velocity field is just the following. You travel backwards in time, so to speak, along your current velocity. You end up somewhere, and then you use some sort of interpolation of the quantity you want to advect onto that point, and then just copy it to that point here to move it forward in time. Okay, so we already computed the backwards trajectories, so now we somehow need to compute them. We put a few temporary results for the neighboring values and locations to perform the interpolation, the exact location where we end up, and a temporary for our interpolated quantity. And here is the actual consumption, so no black magic there. We just travel along, sorry, no, we don't need to travel, but we can directly look up where we ended up when we computed the backwards trajectories. We compute the exact location, interpolate onto that location, and copy this to the new temperature field, or whatever you want to advect, be it temperature or pollen concentration or whatever. Okay, and now, now I'm giving the word to Giacomo. Are you? Oh, wait, I probably should stop sharing, huh?
Thank you.
Okay.
Okay, I will share the screen now. Can you all see?
Yeah, looks good.
Okay, thank you. And thank you, Matthias, for presenting so far. A lot of concepts to talk about. So I will finish the session by talking about parallel model, which is something that so far you have already see, but maybe here we go a bit into detail and we give somehow a formal definition, and then at the end the last topic would be vertical solvers. We're going to try to solve the equation on the vertical. So here, maybe to reiterate a bit on what was said at the beginning, when you deal with a DSL, one of the main differences with, let's say, a general purpose language is that in a DSL you provide some abstractions, you hide some implementation details, which you will not in a general purpose language. I'm thinking about C++, Fortran. There you are on a lower level, so the programmer really needs to explicit every detail of the implementation. While if you provide some abstractions, you hide those details behind the syntax, of course. And thus, it's maybe a good idea to present to you, let's say, the execution model of the DSL to really to be a complement to the explanation of the syntax and of the semantics, to really understand how to use the DSL and to write really complex codes with it. So the execution model, we call it parallel model. I think right now you should have an idea why, because it's inherently parallel. Well, the other purpose is that it works as a reference for when we study optimizations and want to implement them. You can think of it as a correct execution that is your reference, and any optimization, any transformation that you do should lead to code that produces the same effects on the output fields when given the same input field as this execution according to the parallel model. So this is also like a contract with the user in this sense, because the user doesn't really need to worry about what the compiler does as long as it can be, let's say, proven that the execution according to the parallel model is the one that the user expects. Okay, I will proceed. So let's now go into detail. We will look at some Dask pseudocode from the top, so from the stencil definition to the bottom, so to the statements. So below the stencil definition, you have these vertical regions in which you specify the order of iteration. You can also specify, of course, the vertical domain, so over which levels you want to iterate, but here I've hidden this detail. So at this level, you consider these as blocks of codes, and you need to execute these blocks sequentially, one after the other, in the same order in which they are written. Then to execute each block, you of course you need to iterate sequentially through the k levels, as said before. So depending on the order of iteration specified, upward or downward. And this again is a sequential iteration. So within each iteration, so when you fix the k level, you are now looking at a plane, a horizontal domain. You then execute each statement again sequentially in the order in which they are presented. Maybe two remarks here. The statements I refer to are direct children of the region, and yeah, we will see that you can have sub-statements. So here we really think about the outer statements, so the ones that are direct children of the region. And maybe the other remark is that sequential is really strict here in the sense that you need to wait until the first statement is as completely executed to start before you start executing the second. So again, this is a possible execution. This is a model of execution that leads to correct results. But then you will learn that we really don't do things this way because we apply optimizations and relax this thing, but we will see that in a bit. To execute each statement, you need to, of course, go throughout the whole horizontal domain, so throughout the plane in any order. So you iterate in any order through the locations of the same type. They can be edges or they can be cells. And this you do, of course, for each statement. So saying any order means for us this is already a parallel formulation, and this is why we call this parallel model. This you can run on several threads. Each time you encounter a statement, you spawn these threads to execute it over the whole domain. Then you synchronize, then you start with the next statement, and so on. So this is a remark about the more complex statement. Let's take a if then else construct. You can have substatements. So what I said before referred to the statement as a whole. You have to consider it, let's say, atomic. And therefore, if you have a threaded execution, one thread will take this statement as a whole and execute it. So this was already presented, but I reiterate because it is important. We have API fields and temporary fields. Maybe a remark here, we don't have, for example, a const keyword for now to express input fields. We always derive it from the usage. So you can see enf is never written into, so we derive that it's an input field. But maybe for correctness, we could add this feature. It could be interesting. But in any case, the contract, once you derived the type of field, the contract is that we don't write into input fields, of course. We write into output fields and input-output fields, and write the correctly computed value, of course. And input-output fields, we also need to consider what was there before the execution of the stencil. So we need to read from them, of course. Whereas temporary fields are really not part of the contract with the user. So the compiler has full leeway here. They can be lined as shown before or kept allocated. So they are really like local variables. Maybe in C you can think of local variables, and this is up to the compiler. So another remark about a correct execution. On the right-hand side of assignments, when you access a field, when you see a field being referenced, you have to assume the value semantics or copy semantics, meaning that you are accessing the field at the let's say at the location specified as the field was before starting the execution of the statements. So as if you are accessing a copy of the field taken before we started executing f equals sum over and so on. We will clarify why this is important in a bit. So this is the point. This is, let's say, a very constrained way of executing, but it's simple to understand and gives the guarantee that this is what you want to compute. But then to optimize, we need to relax the parallel model. We need to find ways to run faster. So the first of all was already mentioned. removing the sequentiality of k loops. If you instead do it in any order, you iterate through the k loops in any order. You could think of a parallelization opportunity here. Of course, the trivial case is when you don't have vertical data dependency between statements. So you don't have any of these offset accesses, and there you're good to go. Instead, okay, this is a bit more tricky. We will see in detail in the last slide about vertical solver, because there we need to make an important distinction. So let's now try to relax another part of the parallel model, which is the copy semantics. What if we instead assume reference semantics? Meaning that when you access your field, maybe inside a reduction, you are accessing the actual field as it is now in memory. And this leads to dangerous code, because your results, your outputs change depending on in which order the statement is executed over the domain. And we said that we can execute in any order. If you think about this representation of the execution of the statement on two different edges, depending on whether this sum is executed first or this one is executed first, you get different results, and that's not what we want. We really want always the same result. So a threaded execution of this statement could have this problem if you assumed a reference semantic, so you access your field in this way. So instead, a safe way to do this is by field versioning, as Matthias mentioned before. But to really have a good understanding, you can think of a copy of the field just before the statement started. So another relaxation we could do is remove the sequentiality of statements. So one question will be, why would you remove the sequentiality of statements? Again, a possibility could be because I want to do a threaded execution of multiple statements. So each thread would take care of these two statements, although you should notice that they are on different location types. So this statement is on edges, and this statement is on vertices, and this one is on edges. So assuming that one thread could take care of both, because there are enough threads to cover all the vertices or over all the edges. But then you have a problem, because this thread execute concurrently, and you have no guarantee that on one thread you reach statement 2 before all the threads have executed statement 1, because of course we remove this sequentiality. And here again, you can this leads to race conditions again. Is an example with these two statements. This is the second one, computing the gradient of the curl on edge 3, and this is the curl on vertex 0. So again, depending on which of these is executed first, you get different results. And again, this is dangerous, and we want to avoid it. So this concludes the part about the parallel model. Let's jump into vertical solvers. So I think you have seen this before, the heat equation. We want to solve it on the vertical, so on each vertical column of the domain. So we simplify to 1D heat equation. And we apply the discretization. So usually along the vertical, this is implicitly discretized, using backward Euler for time and second order central finite difference for space for the vertical. And this is how it looks like. So maybe a temperature Tn, the vector Tn is the vector of temperatures, of course, over the column at the current time step. And n plus 1 is the next time step. So k plus 1, k minus 1 mean the current level, the one above and the one below. So we are looking just at, let's say, a range one axis. The same equation, recurrence equation rearranged, it looks a bit in this way in a matrix form. So this is the unknown, what we want to calculate, the temperature at the next time step. And in matrix form, this matrix, you should notice that it's a 3-diagonal matrix. So non-zero only on the main diagonal, the one above and the one below, as you can see. So very generally, if you have to solve this system of linear equations expressed in this way, there is a very simple algorithm to solve this in linear time. Linear with respect to the size of the problem. So in this case, how many levels you have. And this is how you solve it with Thomas algorithm. And this is exactly code that we have in our tests, I think. And here you can see that each of the vectors here, so A, B, or C, are repeated for each location of the plane. In this case, I chose edges, but you can do the same for vertices or cells. And therefore, this will solve for each column of your domain. And you see here, I won't go into detail in explaining the Thomas algorithm, but you can look it up if you already don't know it, but it's very simple. There is a forward sweep in which you go from the bottom level to the top level, and a backward sweep, so backwards. And maybe a pattern that you should notice here is that, for example, C depends on C at the level below. So the only dependency is counter loop. You are going upward, but you're looking at the level below. And the same for D. While if you do the opposite, so you go downward, you are looking only at the level above. And this is what we name the solver-like access. Doing this kind of this access, this specific one, f at k minus 1, when you write into f, is a solver-like access, because what you're doing here is you are reading from a value which was written in the previous iteration of the loop, and the same when you iterate in the opposite direction. And this, in these cases, this means that you cannot parallelize the k loop, because for this reason you need to read the value which was written before, and there's no way to parallelize it. While instead, if you look at the value above when you go upward, or below when you go downward, you are looking at the value which was there before the start of the vertical region. So this means you can basically parallelize, because well, you still need to ensure the copy semantics here. Of course, you need to look at a copy of the field before here, but this gives the opportunity to parallelize. Okay, so here we conclude the presentation. Any questions?
Very good. Thanks, Giacomo. Let's see if there are questions. I'm sorry. So questions to either of both presentations, like Matthias on the advanced concept and Giacomo on the private model. So go to the Google Doc and then take the opportunity. So there is already a question from Will. How do you do non-linear operators like flux limiters? So a clarification, basically this boils down to making some sort of distinction based on the current value of a physical quantity. So if wind velocity, for example, is positive or is negative, then take that wind value.
Currently, we don't. We currently we can indeed not do this in dusk or dawn. And we looked at the icon dichromacy stuff we're interested in quite a bit, and we can't find it. But yes, we realize that this is actually something which happens in a very wide array of codes. But because it's currently not in the stuff that we would want to parallelize, it's currently not on our radar. But currently, it's different from a reduction, right? It's like, depending on my current value, I either take my right or my left neighbor. And to the best of my knowledge, we currently have no way to emulate this. Correct me if I'm wrong here, guys.
Maybe there could be
Yes.
a way with weights, but I don't know if that will work, if the actualization will work. But maybe we can try that.
I guess we should probably make a distinction between the vertical and the horizontal, right? Probably in the vertical that would be possible already, or correct me if I'm wrong, but we are,
yes,
more referring to...
Sorry, yes, in the vertical it would actually be possible with an index field if you split. But even with an index field, it's currently awkward because it's write protected, right? So you'd need to make that detour to the driver. But still, since we are at least intending to do this, also have index fields in the horizontal, then maybe it might be there might be a way to emulate it the same way after we also took care of the semi-Lagrangian in the horizontal, which we still need to do.
Right. So Will is pointing you to the Daniels advection instead of the dichrome. I'm not sure, Will, maybe you can clarify which advection. What is Daniels advection? Are you talking about Miura's, or we can clarify then offline? Yeah. So he's giving you a pointer to the actual code in the...
Okay, yeah, that would be very interesting. Yeah.